So what we looked at when we talked about buffer overflow, I gave you two basic programs, and this first one just was a kind of a verbose way of showing that when we can overflow one buffer, we can overflow memory on the stack, then it can affect other things on the stack. Well, what are these other things on the stack? Well, we have things like the old value of EBP, we have things like the return address. So when we issue a call instruction, call pushes the return address onto the stack, and then it jumps to that location where that function is located. This is important because then when that function returns, it's looking for that address on the stack. It's a fundamental, important property with the way that we use the stack. Well, if we can overwrite that, then we can potentially control the flow of the program, and we can inject code and get this program to now execute what we want it to. So that's what we're going to look at today, is how can we continue to kind of overflow that buffer to overwrite that return address, EIP, and then also inject some shellcode so that we can do something arbitrary like pop calculator. So this is the Stack Overflow program, and just make a couple of slight modifications here. So we're going to we'll look at this initially. We have our main program, our main method here, and then we have a function check authentication and argv. So when we call a program, we can access arguments that we pass to it when we invoke it from the command line using this argv. It's an array of char pointers. So when we run this program, we're going to check whatever we pass to the program using argv. So that's called stack overflow1.exe, and if I provided a value of Josh, right, then that's what's going to be passed to this check authentication function. And you'll see it says access denied. If I pass it a value of password1 exclamation, then we'd see that it gave me access granted because those strings match. So it's going to call that method. Inside this method, it's going to take that command line string value and it's going to copy it into this buffer using string copy. Right? So this is very contrived in order to show a buffer overflow. So the problem that we run into, and this is what we went over in the last video, or the video we talked about buffer overflow, is that if we provide a bigger string, a longer string than we have a buffer for, then we can start to overwrite contents on the stack. This string copy doesn't do any bounds checking. It doesn't say, I'm copying password, this value that was supplied, into this buffer. The buffer is only 16 bytes. With a null terminator, we only have 15. So it doesn't do anything. It just starts copying, and that's where it has the ability then to clobber over the contents in memory, the contents on the stack. Okay, so how do we further exploit this? How does this turn into an actual problem in our program? Well, what we want to do then with this classic overflow, and again, there's protections that are built into the compilers and to operating systems and things now that help to prevent this, even when the programmer doesn't do anything to prevent it. And I'm skipping over all of that to show how the classic buffer overflow works. So when we want to try to determine if this program, if there's a problem with it, then what we do is we see that when we run the program, we can provide user input. Well, we want to send a large amount of data in to that program and see if we can get it to crash. So I'm going to have two windows open here. My developer tools command prompt, which comes with Visual Studio. So when you install, you can see I'm using a really dated version here, but when you install Visual Studio, which is an IDE, an integrated development environment, then you get the Visual Studio command prompt. It's different than your normal command prompt in that it adds to the path a bunch of tools like the C compiler on Windows, okay, which is CL. So I'm going to have this open, and what I'm going to use this to do is to, for the most part, I'm going to use it to build my C program. So just like we use GCC in Linux, we can use CL and then the name of the C file to build the resulting a.out. In this case, it's going to be the name of the file .exe, so stack overflow1.exe. There are some additional command line arguments that I'm providing here, and these are compiler arguments. And so this first one disables the guard check, the guard cookie, and that's something that I don't want to get into the details now. We'll talk about it if you take 444 with me. But it helps. It's one of the protections that I mentioned earlier that gets built into the compiler now that helps to prevent these type of overflows. We're going to disable that though. So like I said, this is an ideal scenario for a buffer overflow. I'm also going to produce some debug, what are called debug symbols. And we're going to talk about and look at a different debugger today, very similar to GDB, except it's one provided by Microsoft and it has a graphical interface, so it is probably easier to use. Okay, and these debug symbols just help us that when we're running that program in the debugger, it just helps us to be able to, one, it maps it to the source code, so we'll see the original source code of this file as we step through it, and other things like it understands then in the debugger that I have a main method and that I have a check authentication method and things like that. Again, debug symbols are something we get much deeper into in 444. Okay, the other window I'll have open is Sigwind, and the only reason I'm really using that is because I'm going to run my debugger. It's called WinDebug, and when I run the WinDebug, the name of the program that I want to debug, so Stack Overflow 1.exe, this would be like doing GDB and then the name of the program. I'm going to use Python in order to provide the input for this program. So what you can do with a bash type environment, a bash type shell, is I can say $parentheses, and then I can execute Python inside of there. And so that Python, whatever Python I generate here, that'll become now the value for the argument to this program. So it just makes it a lot easier to work with these type of overflows. Okay, so the first thing I want to do is I want to try to get this program to crash. I want to see if there is in fact an overflow problem. And how I would go about doing that would be to simply send a large amount of data to that program. Okay, so what I can do now is I can run the program and provide it just a large amount of data. So print A times 50. Okay, so Python, this will say invoke Python interpreter -c and run whatever I provide here as a command line argument. Okay, so print A times 50. Okay, if I run this program, we'll see now that I got a crash report. Stack Overflow 1 has encountered a problem and needs to close. So I can just say I don't want to send the report because I know what's happening there. So that gives us a good indication that a crash happened. The problem is that we really don't know much more than a crash happened. And so what we'll want to do is we'll want to run the program with a debugger. And we could do the same thing with GDB if we wanted to. So now I can say WinDebug, which is the Windows debugger, the name of the program, and then any command line arguments. So I hit enter, and you'll see this program pops up. And initially what will happen with a debugger like this is that it will break before it actually executes the program. And what this is doing, just like we saw with GDB, is allowing me to set breakpoints in the program before it's executed. Right? That's a pretty important step. So a bunch of windows. And I don't want to spend too much time going through those. I think most of them here you'll see will kind of make sense. But this is it's a big tool. It takes a little bit of time to get used to. First thing is we have the disassembly window. So whenever we ran the disassemble command in GDB, this is the same thing, except that it's just always there. We had information about the registers. So we had commands in GDB to dump the register state. These are just always there. They're always visible. This provides us memory, so we can type in any type of address, location, or register, and this will give us information about the memory that's stored in that location, so we could watch memory in real time if we wanted to. The command window with something like GDB is going to be very similar to just typing commands like we did in GDB, and that we can type commands here down in this little prompt, and it'll tell the debugger to do things. So in this case, we just want to see the crash. Since we've attached a debugger to this process and we know it's going to crash, what will happen is I can type G, and that's go, and you've also got, with something like WinDebug, you've also got a file menu to interact with the debugger. And what will happen now is it'll run and it'll crash. It'll crash and our debugger will stop where it crashed. Well, we can see that this looks pretty weird, and that what we have in the disassembly is 41414141. What we have down here, because when the program crashes, it dumps everything to this little command window. We can see EIP. Remember, EIP is the register that has as its value the next location where it's going to begin to execute instructions. And EIP has 41414141, which is all those A's. And so what we have shown now in catching this crash with the debugger is that we overwrote the stack with A's, and more importantly, we overwrote the return address with A's. So we can see that when the program crashes and the value in EIP when it crashes is something that we provided. That means that we can take control over EIP. So what we want to figure out is how much of the stack do we need to actually overwrite in order to overwrite the return address, in order to put a value directly into EIP when that function returns. So there's a variety of ways we can do that. And just to not make this video too lengthy, we're just going to look at the original source. Okay, most of the time you're going to be doing this, reverse engineering type stuff. You're probably not going to have the source, but in this case we have it, so we're going to use it. And what we're going to look at doing then is this is the function. So we want to try to figure out how many A's do we have to send in order to overwrite the return address. Well, we have a 16-byte buffer. We have a integer variable before that. Okay, so the local stack space is going to be 16 plus 4. We'll have the prologue. So before stack space is allocated for these two locals, we'll have the old EBP saved. So 16 plus 4, which is 24. And then once we've entered that function, there was a call instruction. There's a call instruction before this check authentication function. So the return address is pushed onto the stack as well. So that gives us 24 bytes, 24 A's before we overwrite the return address. Okay, so how could we test that? Well, we could take this sample code right here, and what we want to do is we want to add a value, like, let's try a different character. B. 41 is the ASCII value of A. Okay, so that's why 41 is showing up, and that's why that's important. Well, let's say, if I say it's 24 characters, 24 bytes, to overwrite everything up to the old value of EBP, and then it's 4 more bytes to overwrite EIP, that return address. So we'll do 24 A's and then 4 B's. And what we're looking for now is that when the program crashes, we have exactly those 4 bytes of data where we want, right inside of EIP, right, to overwrite that return address. So in this case, I want to see, instead of 41414141 in EIP, I want to see 42424242. So we'll run the program again. I'll just type G for go. And you can see now when it crashes, EIP, we can see that here in the dump in this command window. We can also see it up here in the dump in this registers window. We can also see here in the disassembly. 42424242. So we calculated the layout of the stack correctly, and we have complete control over EIP. And this is kind of what the exploitation is all about. Understanding the overflow is that we understood how that stack was laid out, what was occupying the memory, the contents of the stack, and we were able to craft a payload that precisely overwrote the return address, right? And that's really what it's all about. So another thing that you'll commonly see when it comes to exploitation is not necessarily you'll always write Python like this. That likely what you'll do, or may find very helpful, is that you'll write a little Python script, and the Python script will generate your output, and you'll just feed that into the program. So here I've got overflow.py, and here's an example of my stack. So here you can see just what we talked about previously as a comment there, so I can upload this file, and if I forget, just please remind me. But we have the buffer. Okay, the buffer was the last local variable, so this is going to be allocated last. Space for that's going to be allocated last, so that's going to be on the top of the stack. The auth flag comes next, then old EBP, and then the return address. So here we have the buffer plus the auth flag plus the old value of EBP, and then EIP, or the return address, right? Lower addresses, higher addresses. Okay, and that's how those local variables are going to be allocated on the stack. Right? The buffer was last, then that variable auth flag, then old EBP, then EIP. Okay, so what we can do with this, ignore all this stuff here just for a moment. What we can do with this is I can say, okay, payload equals A times 24 plus B times 4. So the same thing that I just did, except I'm putting it inside of this Python script. And now with this script, I'll just do print payload. So now instead of having that print statement here in the command line, I can say Python overflow.py. So it's going to execute that script, and all the script is going to do is it's going to print the value of payload, which is A times 24, B times 4. Okay, so if I got everything right, we're going to see the same results here. Simply that it's going to crash with a value of B's in EIP, which it did. Okay, so that's really the first important step, is that we now know that we control the flow of the program, control execution simply by, because we can overwrite EIP. Now, one thing that I want to do with this program is I want to make this buffer a little bit larger. So I'm going to make this a 512 byte buffer because I just want it to be plenty big. So now when we talk about shellcode, we have space to put our shellcode in. Okay, so I'm going to change that value. Go to the Visual Studio command prompt, and I'm going to build the program again, compile it. Okay, and now what has to happen is we need to figure out how large is that buffer, right? Because we just changed it. And one thing that you'll notice if you do this more, if you get into exploitation and reverse engineering more, is that just because I said this was 512 bytes doesn't mean it always is. Okay, so let's start with that. We know the value 512, and we can really kind of go through the same process here. I can say 512 plus 4 bytes for the off flag plus 4 bytes for old EBP. So 512 plus 4 is 16 plus 4 is 520. Okay, so now I can change this script to be 520 A's and 4 B's. And now I can save it, and I can run that through with WinDebug, and we can see what happens. Okay, EIP has this. It still crashed, something still happened, but it's not quite right. Okay, we can see we've got 42424242 and just some weird stuff. So what this is telling us right now is that we didn't quite get it right. 520 is not quite right. So I'm going to add 524. Okay, just kind of a guess. We'll run it again. Let it crash, and there we go. We've got control again. 424242. So these are in EIP. Okay, so what will happen sometimes is the compiler, for a variety of reasons, might make this buffer larger than you originally allocated, and it might do that for a variety of reasons, such as a stack alignment. So it's worth noting at this point in time, at the stage of understanding how this works, that just because this is 512 doesn't mean that's how large it's actually going to be. It could be a little bit larger. The compiler will do things that you may or may not understand. So sometimes it takes a little bit more guessing, or opening up the program and disassembling it. Right? We could do that with GDB or with WinDebug, either one, and we could step through there. We could see this, how much is actually being allocated on the stack for it. In this case, we were able to just guess, and so that worked out just as well for us. Okay, so that's great. This is proof of concept. We know that we're in control. The next thing that we want to do is to execute code, and that's where the shellcode comes in. So what is shellcode? Well, in the simplest sense, shellcode is it's something like this. Here's two examples of shellcode. And all it really is, what it really boils down to, is that it's the resulting opcodes from our assembly instructions. So we can look at, for example, let's take a look at, there's this utility called object dump. And you can use object dump to disassemble an object file. And an object file is the resulting, essentially the resulting binary from when you compile a program. So I can say object jump -d, stack overflow, make this a little bit larger, 1.obg. Okay, so when you use Visual Studio to compile, you'll get an object file. And there's a variety of ways you can get this information. But what we're looking at, we could open up and disassemble, get the same information. But what we're really looking at is these are the opcodes that are the result. This is what this opcode represents, this instruction, right? So 55 represents push EBP. 8BEC represents move into ESP EBP. And so our shellcode is just opcodes. And those opcodes represent assembly instructions. So that's how you build shellcode. Now, the trick of it is to build shellcode that works, that you're able to inject into a program and get it to run on that, whatever system that program happens to be running on. So we're going to look at a relatively contrived example. and this is going to be used to pop calculator. We just want to get calculator to launch. So one function that we can call, and this takes us to MSDN, which is the Microsoft Developer Network. There are a lot of Windows API function calls, the Windows API. And so if you really want to get into writing shellcode and exploitation and reverse engineering, you have to spend some time learning the Windows API. One function that we're going to look at in order to build our shellcode is called winexec. And what this will do is it'll run the specified application. So we're going to call and use winexec to launch calc.exe. So in order to call winexec as a function, we have to provide two arguments. The command line, so a string value, which will just be calc.exe, and then whether we want that to show. So we'll just hard code that value. MSDN and all the functions that are labeled. So if you want to call a Windows API function, you come to MSDN and you can figure out how to do that. So how does that look? Well, these are two ways in which we could write this in assembly. And you've got to think about a couple things here. That is, we're getting ready to call winexec. And so in order to do that, we have to push two values onto the stack. This string, and then a value for command show. And so what we can do in our shellcode in order to do that, as you can see, we can do push.exe, push.calc. Okay. Remember, we're on a 32-bit system. So on a 32-bit system, our stack is only 4 bytes. Right? Each character here represents a byte. So we're going to push calc and then .exe, two different pushes, because we need to have that split up two different over 4 bytes. Okay. This expects a pointer to a string for the first argument. So what we're going to do is we're going to move. So we're going to push, and then we're going to move into ESP. Right? Well, ESP points to the top of our stack. So after we've pushed these two values, ESP is essentially a pointer to the beginning of the string. ESP is going to be an address that points to the beginning of the string, the top of our stack. So we move that into EAX. We push 1, okay, because we pushed the last argument first. So command show 1, so that means show whatever we're about to run or execute. And then we push EAX, which is a pointer to the string. The last thing that we do is we move this value into EBX and then call EBX. So we've looked at calling functions that have labels, but we can also call registers. And whatever we provide in that register needs to be an address. So what is this 7C862AED? Well, that's the address in one of the libraries where the winexec function is. So what we're doing here is that's loading the address for winexec into EBX, and that's allowing us to call EBX. Okay, I put wrong above this, and the reason that is wrong is this right here. The problem that we're going to run into is that we need to null terminate that string, which is not being done here. Calc.exe, and there's no null terminator. So when this goes to read this value, it's going to start reading these characters, and it's going to go until it finds a null termination, which is not going to be at the end of our string. So it's going to likely not work. It's going to fail. So how can we fix something like that? Well, you could do a push 0, because that's really what we want. We want to push a null termination on. The problem with that is, though, we're dealing with an overflow in a string function. And so if part of our shellcode contains a null termination character, because what would this look like? Well, it would look something like, and I might get this wrong, but it would look something like 68 00. Right? That's a null terminator now in our shellcode. And so if this became part of our payload, that string copy is going to copy password. Passwords are payload that's going to contain our shellcode. And if it encounters a null byte, it's going to stop copying. So likely it's going to screw up our shellcode. It's going to screw up our payload, and our exploit's not going to work. So we want to avoid null bytes in our shellcode. So this is a really good reason why someone would do a shellcode developer would do something like this: XOR EAX EAX instead of move EAX 0. So here you can see what we can do is we can XOR a register with itself. That's going to zero out that register. Now we can push EAX, and that's going to push null bytes onto the stack. Right? So now calc.exe null byte is going to be properly null terminated. The other important thing you see here is in all these opcodes, this which becomes our shellcode, there are no null bytes in here. So now this is going to work. So what we'll do now is we'll modify overflow.py to include that shellcode, and we just won't mess around with this stuff that doesn't work. Okay, so here's overflow, here's the shellcode. Metasploit, if you've run across it, Metasploit can be used and is often used to generate shellcode. This is some shellcode generated by Metasploit. It also, I don't think it works, and you'll see why, because there are a lot of null bytes in it. Right, so that doesn't work. So better works, there's no null bytes, and it pops calc. Or at least we hope it does. I hope it does. Okay, so the last thing we have to do now is figure out how to structure this payload in order to get the shellcode to execute and get the calculator to pop. So one of the things that you may or may not have noticed when you run this program is, let's go to the point where it crashes. Oh, whoops. Okay, there you see the shellcode's working. Let's go back to a point where it crashes. Okay, we want to look at the registers. And what we're hoping to find is that we have a register that is pointing to the stack. And when we look at these registers, we see EAX doesn't, EVP doesn't, EIP doesn't. It has a value that looks like it was overwritten, but we need a register that contains an address that points to the stack. So just to make things a little bit more brief, EDX contains this value, 12FD5C. And what we can do is we can, in the memory window, we can just type in EDX, right? And that's going to show us that address that EDX is pointing to. And you can see that that address, 12FD5C, that's actually an address on the stack. And we know that because when we look at this memory window, we have all these A's. And that's really good. Again, it's an ideal situation because what we want to do when we overwrite EIP is we want to be able to transfer execution to our shellcode. And because we have a register that is pointing somewhere on our stack, we can now call that register and that will, or jump to that register. There's kind of two ways. And get it to execute, start executing at this location. Okay, 41414141. We don't want it to do that. We want it to be able to set up our payload in a way where we essentially will create the NOP sled, and from there it'll then execute our shellcode. Because we don't know exactly where this register is pointing to in the stack, in this buffer that we're overflowing. So what we can do, go back to my example here, is I can say, okay, I just want to create, I have 520 characters, right, 520 bytes, and I want to subtract from that the length of this pad. And from there, I also want to subtract the breakpoint and also the length of my shellcode, right? So that'll give me the number of ops. So how do I use that? Well, 90 is the opcode for no op, right? It does nothing. And what we can create here is generally referred to as a NOP sled, so that when we say jump to this address, instead of this being 41414141, which would work as well actually, we hit NOPs, and it executes all those instructions and does nothing, and it just continues to execute those until it hits our shellcode. Okay, so we say we want no ops times this value that we've calculated. Then we want this breakpoint, and with a breakpoint you can have CC. That's our int3. So if we inject a breakpoint, then what that'll do is the debugger will break right before our shellcode. Okay, then I want to add to my payload the shellcode itself, which I called better, then this pad. And all this padding is doing is ensuring that we have 528 bytes total, because we need to have that so that when we overwrite the return address, when we overwrite EIP, it overwrites in the correct location, right? We determine that 524 plus 4. So I think I need to add one more to that. 524 plus 4. No, that was right. This was wrong. Well, anyways, if I screwed up, I'll fix it. Okay, and then finally a return address. And this is the last kind of tricky bit in getting this overflow to work, is that how do we know what address to put there? Before we just had a bunch of B's, and that doesn't do anything for us. Well, we've determined that EDX is a register that points to our stack. So what we want to do is we want to be able to transfer execution to this address. So how could we do that? Well, we could call EDX, or we could jump EDX. Either way, we'll go to this address and we'll start executing instructions, which will be our NOPs, followed by a break, followed by the shellcode, followed by the padding. So there's a variety of ways and techniques to do this. I think to get started, one of the easiest is to simply use the debugger. So if we go to our command tool down here, what we want to do is we want to look at the loaded modules. LM is a command that shows the loaded modules. We talked at the beginning of the semester about virtual address and the address space of a program. And so when this program is loaded, you can see that the program itself is at these addresses, from 400,000 to 40F000. Okay, that's the address space for the program itself. Those are all the addresses for the instructions for that program. This also included a library called kernel32 and NTDLL, okay, which are Windows OS libraries. So we want to be able to find, I'm going to restart this program, we want to be able to find an instruction somewhere in the address space in this program that is a call EDX. So first thing we can figure out is what are the opcodes. Well, with WinDebug, if you type in A, that takes us into assembly mode. So now I can type in an instruction, call EDX, hit enter, that exits that input mode, and it replaces wherever my cursor was with the assembly instruction that I just typed. Okay, so that just replaced that int3 with a call EDX. Okay, the important thing is here are all our opcodes. So the opcode for call EDX, no, I think it was call EDX, wasn't it? So let's go back and do that again. So A, call EDX, enter, enter. Okay, there's the opcode. So either way, I believe it's EDX. So you can see the opcode is FFD2. Okay, so now with that opcode, what I can do is I can go back to this command window and I can do S, which is search. I can give it a start address and an end address. So we'll search the entire address space for a program, and then the opcode, so FFD2. And what will happen here is we get no output. So that's a problem. We can't use the program itself. So we have other libraries that have been loaded, so we can use those. So let's just use kernel32. So that's 7C80, 7C800000 to 7C8F6000. Okay, and there we go. Now we got some results. So you can see that it found that opcode FFD2 at this address, 7C87B432. So what we do with that address now is that becomes 7C87B432. That becomes this return address. That's what we're going to overwrite EIP with, that return address. So that address is getting loaded into EIP. EIP then is going to call EDX. EDX has the address for the stack, so it's going to call to that address, which is on the stack, and then it's going to start executing the rest of our payload. So that's what this thing looks like in its entirety. So now I can get rid of this payload, and we can do the real thing. Okay, so we'll have NOPs, followed by a breakpoint, followed by our shellcode, followed by our pad, and then the return address to overwrite the return address to control the flow of execution of this program. Okay, so I'm going to close WinDebug, and we'll run this one more time. Okay, so debugger started, it broke, so the program has not executed yet. This is giving us a chance to set any breakpoints if we wanted to. In this case, we don't. And what I hope to see happen is that when it runs, it will break on the breakpoint that I provided. Right? I put a breakpoint right before the shellcode. So if I got everything right and did all the calculations correctly here, I'm going to run this, and there we go. You can see there's my NOP sled. Right? So there's all those NOPs. So that address that did call EDX worked. It called that address, which was on the stack somewhere. The stack was filled with no ops. So the CPU just executed that no op until it hit my int3. Now from there, we have the shellcode. So all that stuff that we talked about before, you can see there's the instruction as well as the opcode. And that's the shellcode. So if we wanted to, now we could step through it. And we're getting ready for the move. Okay, and there's the call to EBX. And there's our calculator, right? And then we're done. From there, the rest of my NOPs, which is the padding, and the program eventually crashes. Okay, let's see how we're doing on time. Oh yeah, that's plenty long. So anyways, I know this was a lot to take in one video, so I would encourage you to watch it a couple times. I would really encourage you to go through this example as well. And if you need the code and I forget to upload it or something, please just email me. We'd be more than happy to send it to you. Just to understand and really go through a basic Stack Overflow. Because they are the foundation for a lot of modern day security techniques that are in place now to mitigate and kind of understanding the history of how exploitation has occurred, or what, where did it all start, and what has the industry done to stop this type of exploitation will give you a better understanding with things like the Windows 10. Windows 10 has something called Control Flow Guard, and it's the latest in mitigations to help prevent things like this. So anyways, it's well beyond the scope of 3.14, but I just wanted to leave you with that. So let me know if you have any questions or any problems running this. I can't provide you with the VM, but again, we'll do plenty of this in 4.44. So if anything, hopefully that gives you something to look forward to. That's it. I hope everyone had a great semester. Please take some time to fill out the student opinion survey, and I will talk to you guys hopefully in a class in the future. Thanks.